So, on December 7th, 1972, as the Apollo 17 was tearing through space on its last moon mission, a crew member pointed his Hasselblad camera out of the window to capture what has become the most widely reproduced image in history. The very first full-color, fully illuminated image of Earth from space. This image captivated the world, and it became a symbol of the environmental movement. After decades of unregulated pollution that produced burning rivers and Love Canal, things were starting to change. We began to understand that the planet was a system in a finite sphere that supported life. And during this time, the United States passed some of its most important and lasting environmental protections, such as the Clean Water Act, the Clean Air Act, the Endangered Species Act, and the Environmental Protection Agency was formed. And things got better. But if there's one thing to know about our planet, it doesn't stop changing. The systems that sustain life are connected to even greater systems that shape the planet itself, all of which are dynamic. The Earth has gone through extraordinary changes since it first coalesced out of space dust 4.5 billion years ago. But as cataclysmic as some of those changes have been, they've not been random, but rather consequences of a system of cause and effect. So what can the changes of the past tell us about how these systems work? And how is our global drive for energy and consumption positioning us as one of the greatest agents of change the planet has known? I was born in 1969, and I can tell you I never heard the phrase parts per million once in my childhood. As I graduated high school in 1987, I still had no idea what parts per million were, even though that was the same year that the planet would surpass what scientists call the safe level of atmospheric CO2. I started teaching in 1997, and by then I had learned a lot about climate change. It was the year of the Kyoto Protocol, the very first binding treaty requiring nations to reduce their carbon emissions. In 2000, I joined the science department here at Fieldston. And since then, I've been teaching students about the connection between climate and carbon. So how does all this change add up? That's a lot of change in my lifetime. In fact, it's estimated that since the Industrial Revolution, we've added about 50% more CO2 into the atmosphere. Is that a lot? How does that compare to the past? Turns out, it's a lot. The ice core data tell us that the current CO2 levels are the highest they've been in the last 800,000 years. And, as it turns out, CO2 levels in the atmosphere are highly correlated with temperature over that time. Speaking of temperature, this slide is a fascinating look back on the Earth's history of past temperature. Noting that the scale shifts from thousands of years on the right to millions of years on the left, what you can see is that the early Earth is marked by these dramatic swings of temperature, from boiling oceans to miles of ice. But what I found most interesting about this graph is this flat line on the right-hand side, right by the present, called the Holocene climate optimum, dubbed as Earth's Goldilocks zone. This is the period of time that has supported the development of agriculture, cities, industry, and technology. But is precisely the fruits of human civilization that currently put the levers of future climate change in our hands. So what can we learn about the deep past that can tell us about how these systems will play out in the future? Let's go back to a much earlier time, 370 million years ago to the Devonian period. At this time, at the southern hemisphere of the globe, we see this ancient continent of Gondwana, but there's no animal life there. All the life was in the sea. Known as the Age of Fish, the oceans were teeming with these armored monsters called placoderms. The tetrapods, our four-limbed ancestors, hadn't even stepped out onto land yet. On land, however, ancient trees were taking root. 100-foot-tall Archaeopterysts were beginning their ascent, developing root systems that pulverized the rocks, releasing minerals that formed the first soil. These soils quickly washed into the ocean and began one of the greatest mass extinction events the Earth has known. This phosphorus-rich runoff caused spikes of algae blooms, which died and decayed in a process called eutrophication. The decomposing bacteria sucked the oxygen out, and 70% of marine life died of anoxia. Meanwhile, the runaway success of these trees sucked so much CO2 out of the atmosphere that the planet plunged into a 100-million-year cooling period known as the Ice House. The planet bloomed, and then it froze. Okay, well, if drops in CO2 can cool the planet, then spikes in CO2 will certainly heat it. Let's fast forward to the Permian 252 million years ago. At this time, we have the supercontinent Pangaea. It is covered by forests, but it's dominated by a diversity of reptiles, including this one, our ancient ancestor, the warm-blooded proto-mammal Lystroceros, which literally means shovel lizard. Turns out that's actually going to be a good thing. These animals could burrow underground and live under there, which is where they stayed to basically survive the events that are about to unfold. By the end of the Permian, more than 90% of life on the planet is gone. Known as the Great Dying, it began with the volcanoes of the Siberian Traps, an inferno of lava fields that span more than 3,000 square miles, burned for more than 2 million years, and emitted over 200,000 gigatons of carbon. With carbon dioxide quadrupling, the oceans warmed too. In fact, the oceans warmed so much that it brought circulation to a halt. And there was a bacteria that thrived in this anoxic ocean, and it produced a toxic waste product called hydrogen sulfide, a gas so lethal that we can detect its rotting egg smell in concentrations of less than 1 part per million. Scientists hypothesize that bubbles of hydrogen sulfide came to the surface of the ocean and wiped out life on land in its wake, except for that proto-mammal, that was the shovel lizard. But here we are still. The survivors of the Permian would go on to survive 2 more mass extinctions before diversifying into all the life forms we know today. So what are the lessons of these past extinctions? The planet changes. It's a dynamic system, and we are just beginning to understand its complexity. But we know this to be true. Carbon and climate go hand in hand. To quote the paleontologist Peter Ward, whether it's volcanoes or volvos, emitting large amounts of carbon dioxide have dire consequences. In fact, we also know this to be true. The rate at which we are releasing carbon dioxide today is 40 times greater than the Permian extinction period. As I was preparing for this talk, and I was looking up the history of this picture, I realized that as iconic as it is not without its criticism. Perhaps this anthropocentric God's eye view of a detached and solitary orb in a vast emptiness from the lens of a human in space is not the inspiration that we need for facing the problems brought to us by the Anthropocene. Maybe the inspiration for the next wave of change will come from the ground, from connection, from an appreciation that we are part of this dynamic system and not apart from it. Maybe it will look like this. Do you remember what it's like to fall in love with a place? Its mud and its trees and its insects, its secrets and its discoveries. In the words of the Oberlin professor, environmental educator David Orr, the world does not need more successful people. Indeed, it is the relentless pursuit of success that has unleashed this ancient carbon. No, what the world needs, he tells us, are healers and restorers, storytellers and lovers. It needs people who will live well in their place, and it needs people of moral courage willing to fight to make the world habitable and humane. And these needs have very little to do with success as our culture has come to define it. It is not the first time that the planet has changed. And it's not the first time that life itself has driven these changes. But it is the first time that we are the agents of change. We are the trees of the Devonian. We are the volcanoes of the Permian. The levers for change are in our hands. Thank you.